So we talked about the different types of stress and how to calculate it. Let's talk about the second half of this lesson, which is strain. Now, strain is denoted by the Greek symbol epsilon, which looks like a backwards 3. And what strain is the change in length or shape, and I'll go ahead and put shape in parentheses, so in length, or we could say shape, due to outside forces. And the symbol, or the formula for strain, I'll go ahead and write it out. Wait a second before you write it out. Let me show you how to draw the symbols, because one of them are brand new to you. It is delta, which looks kind of like a cherry, divided by the length original. Let me show you off to the side a couple times how I draw it. I draw this little C, and then I bring it back and go over, right? You could just draw a circle and have a little tick coming out of it, just make it look kind of like a cherry. That's also acceptable. So I'll draw it one more time in case you need me to see it. Draw a little circle with a little tick coming out of it like that. You don't have to draw all that, just letting you know how to draw it. So what does that delta symbol mean? Well, that little symbol means change in length. How much did it change in length when you applied a force to it? And LO stands for original length. How original, right? Yeah, you see what I did there? It's pretty good. It's been kind of a stressful day. Right? Good one, Anderson. So, as you can imagine, guys, when you, well, let's use this. When you put enough pressure on something, you can imagine when you compress it, it'll change in length a little bit. When you pull it apart, it'll expand a little bit, changes in length. That's what it's talking about. Fair enough? So let's go back to our original example, which was member AD. Y'all might remember member AD. We calculated its stress already. What did we get for its stress? We got 711 PSI, that member that we're talking about. Let's go ahead and redraw it. Actually, I shouldn't draw PSI lowercase, but whatever. Doesn't really make that big a deal. I'm going to draw the member as a rectangle so we can imagine this actual 1x2. Right? The ones that we use when we built our bridges. And most of them were cut in about 2 feet lengths, right? Let's go ahead and make that our standard. Let's say that's our original length. So LO, length original, is 2 feet. And let's say the change in length, so this little delta, equals very small, 0.05 inches. So 1/20th of an inch. And that's believable. It's a very small change, right? It barely changes in length at all when we compress it. Hardly noticeable. Could y'all imagine that? Is that feasible? Good. So what would be our actual strain? So we plug it in. We'd say epsilon equals delta divided by, let's move it out, delta divided by length original, which is equal to 0.05 inches divided by 24 inches. I'm glad you recognize that it would be in inches, because we need to use the same unit. It is 2 feet, but 2 feet is equal to 24 inches. And I'll go ahead and separate that so we know those aren't the same thing. So you have to convert it to inches, right? Now I got a question for you. When you convert something to inches, what happens? Or, I'm sorry, when you divide inches by inches, when we convert it to inches, now it's inches over inches. They cancel out. So what's our unit? Nothing. And when you type it in your handy dandy calculator, you get about epsilon equals 0.0021. And no, it's nothing. Because it's a ratio, it's a proportion. It's the percentage, well, not the percentage, but it's the amount it changed in length. It means it changed in length about 0.2%, which is nothing. And that's kind of the point. Does that make sense to everybody? Let's make a couple notes for ourselves. The first note I want to make is strain has no units. And it makes sense that it would have no units. And the last thing I want to point out to you is when you calculate strain, you just find anywhere to write this. But strain is usually a very small number, which also makes sense because the change in length when you apply a force, unless it's a rubber band, wouldn't change very much for the most part. So you should get a very small number for strain. So if you're calculating strain and you get 3,000, you're probably wrong. Look at it again. Make sense?